Hi, everybody. We're going to play a little more Zelda Wave for you after we get to the break. I know that one's a very popular one. Like, I've had students request that, just like, please play Zelda Wave. And I'm like, oh yeah, I will definitely play that because it's really good. Also to celebrate me starting Breath of the Wild, 5 years after it came out. So. Oh, and also Maya is here. Hi, Maya. Maya, say hi. Maya, say hi. I don't know if you can hear her. Hold on. Maya, say hi. Oops, hold on. There you go. Say hi. Hi. Okay, now go away. Alright, what are we doing this week? Oh, we have so much to do this week. So, there's 2 weeks that kind of suck. Sorry, I'm still adjusting my mic here. And this is one of them, and that's because week 5 is an exam week. What are exams? Exams are basically your quizzes stapled together. And you've had 3 quizzes so far. There's a 4th quiz on Unit 7 and 8, which we're going to talk about a little bit later. But you do have an exam, and the exam is on Friday. So that's the date posted in the syllabus. And I realized that, well, wait a second, there isn't a class scheduled on Friday. Well, there's an exam scheduled on Friday, but you might not have known that, or something came up, or I don't know, something like that. So what I do for exam scheduling is, if you need me to move the exam for you personally, forward or backwards one day. So if you'd rather take it on Thursday or you'd rather take it on Saturday, you can email me and let me know, and I can make that accommodation for you. It's got to be within 24 hours of when I hit the button for everybody. So you can't take the exam tomorrow, nor can you take it next week. It's got to be either Thursday, Friday, or Saturday. It's scheduled for Friday, so if you're okay with taking it on Friday, don't email me. It'll open up automatically. If you need it earlier or later, and it could be for any reason. You don't need to show me like, oh, I'm working, or I have a doctor appointment, or whatever. It doesn't matter. Just like, if you need an extra day to study, just email me and tell me, hey, can I do Saturday? Sure, whatever, I could do that. I can't do Sunday because I have to get all the scores in and processed in a timely manner. So the exam will cover units 1 through 8. We're going to finish unit 7 today. And unit 8's real short. And then we have Wednesday for a review session, basically, or a little bit of lecture if we don't quite get there. We'll talk about the quiz for Unit 7 and 8 later, and how that's a little bit different than previous quizzes in terms of, like, answers being released, because there's no time. We'll talk about that again when we get there. Quiz number 3 is due tonight. Make sure you get that in by the deadline. And then lab worksheet number 2 is due on Wednesday. Not as many questions in the chat about lab worksheet number 2. So hopefully everybody is doing okay on that. Remember, if you get stuck on something, or like you aren't sure if your graph is plotted correctly or whatever, paste a picture in the class Discord, and you could talk to other people about it. Like, that's totally fine. You just can't copy somebody else's graph. And obviously, if you did, I would know, because you'd have a picture of a graph and not an actual graph in there. All right, so today we're going to talk about atoms. We're going to talk about what atoms look like, and then we're going to describe a bunch of ways to, describe them. So here we go. Let's do that. There's your picture of an atom. This is not an accurate picture. Remember that the nucleus of the atom is extremely tiny, and that the electron cloud relative to it is still tiny, but some 10,000 times bigger. So in the nucleus, which we have zoomed way, way, way in here, we have little tiny parts. Now, the electron cloud has very little matter because electrons are very light. I think I'm missing something in your translation there. I'm not sure what you mean by final reminder thing, and then they... Huh? Sorry. Can you type that out for me again? So on the outside, we have a little teeny tiny pieces of matter floating around. But on the inside... Oh, when is it close? Okay. Yes, so there is one extra day for all assignments. The only exception is the exam. The exam is open for 24 hours and then it's closed. Sorry, I apologize. In our atom here, in the nucleus, which is the central part where most of the matter is, we have our protons and neutrons, and that is extremely dense. Now, you may have heard of something called like a neutron star, which is like a teaspoon of neutron star would be 1 billion tons or something absurd like that. That's basically how atoms are. If atoms were completely solid, everything would weigh billions of tons. Because the matter is just so tightly packed in there together. But the vast majority of the space in the atom is empty, and so we don't weigh billions of tons. We just weigh kilograms, on the order of kilograms, we'll say. Now, of the parts of the atom, the nucleus is stationary. It does not move. It's just sort of like the Earth relative to, say, the moon. The moon orbits the Earth, and if we consider the Earth to be stationary, the moon would be moving. On the screen here, you'll see that my electrons are on the outside, and they have these like little rings drawn in here. And it's very important to note that this is just a model, and that there are not actually constrained paths for my electrons to go. They can go wherever they want to around the nucleus. So this electron right here might end up having an orbit that's kind of like this. And then maybe it goes over here a bit. Its orbit is very chaotic. But what's important is that it goes in some prescribed region, and that region that it travels is called the electron cloud. And again, the electron can take any path it wants to, and we'll talk about that much more in 161. All you need to know is that nucleus is the center, everything else is the electron cloud. Now, in the nucleus, there are two types of things. These are called nucleons, and they have the following properties. So, first we have the proton, and you'll notice that there's a little plus sign on my proton, and then I have a neutron, and there's no symbol at all. The plus and minus symbols represent a fundamental property that this matter contains, and it's called charge. Now, everyone's familiar with charge because we've all seen lightning, we've all plugged things into the wall, we've all maybe gotten like zapped when we walked across a fuzzy or shaggy carpet and then touched, I don't know, something metal or another person to zap them. And it's all due to charge. It's all due to electrons. There are two different types of charges here. And we have arbitrarily assigned them positive and negative. Now, this is just so math works when we do calculations involving charge. But positive isn't good charge and negative isn't bad charge. In fact, the negative charge is what moves around. Thanks, Benjamin Franklin. You got that wrong. Benjamin Franklin thought it was positive charges that move. I believe that's how the legend goes. And then it turns out all of physics is backwards because of that. Anyway, these two charges are fundamental and opposite in terms of their sign and have the following properties. If I take two entities that have different charges and I place them next to each other, they will attract. But if I place two entities with the same charge next to each other, they repel apart. And this is true whether it's positive or negative. So, like charges repel, I guess we'll write that down. And then opposite charges attract. And you've probably heard the expression opposites attract. It comes from physics, because physicists make very good memes, I guess. I don't know. Now, the neutron is kind of weird. And that's because the neutron is just there to act like nuclear glue. It does not have any charge present. A neutron walks into a bar. How much for a drink? He asked the bartender. For you, sir, no charge. No charge. Because he's a neutron. Thank you, I'll be here all quarter. So what the hell do neutrons do then? It turns out that there are other forces that are in the atom, and we're only going to concern ourselves with the charge force. There are other nuclear forces at play. You may have heard of something called the weak nuclear force and the strong nuclear force. This is one of those. Neutrons interact with other matter, such as protons, through the strong nuclear force, and it ends up acting like nuclear glue. So neutrons are necessary for the atom to prevent itself from falling apart, kind of like Mega Man does when he explodes and dies. Because all those protons in the middle, they're all positively charged, and they're all repelling each other. So the neutrons counteract that. They hold the nucleus together more strongly than the protons can repel each other. And so that's why nuclei stick. But that's as far as we're going to go with the description of how does the nucleus remain held together, because that's about all I know. I'm not a physicist. I've never studied quarks or the weak or strong nuclear forces. I just know the bare basics. Because that's not what interests us as chemists. We care much more about the positive-negative interaction between the nucleus and electrons, and then also electrons and other electrons in chemistry. So that's our general slide about what the nucleus looks like, as well as the electrons that are buzzing around the outside. Now you're going to notice that I put the word atoms here in italics, and that's because this is an important word to note here. Atoms are always electrically neutral. What that means is that the number of protons and electrons in the atom have to be the same number. So in this carbon atom here, you'll notice that I've written this out here, 6 protons and 6 neutrons. If I were to add all the charges together, so here are my protons, which I could sum together like that. This is what I'm listening to. Yes, you're right there. Very good. My cat is in my ear meowing. Here's all my electrons. And if I add those together, I get 6 minus. And if I were to add these values together, positive 6 and negative 6, I get the total charge, which is 0. Maya says, oh, Maya ran away. Maya is sneaky like that. But she says hi back. There we go. So in an atom, the charge is electrically neutral. Remember that, because immediately what we're going to do in the next section is we're going to try and make things that are not electrically neutral, because that's interesting to us. So if you have the same number of protons and electrons, you have a neutral atom. Now, it's hard to remove protons because the nucleus is pretty much fixed, so we can't really do much to this. But it's easy to remove electrons. It's also easy to add them. You could go in either direction. It just depends on what you're trying to do. If you're trying to remove electrons, you do things like rubbing a material against another surface, and the electrons will get pushed off just by that force. So this is why you rub things like a balloon against, say, your hair, and then you collect and accumulate a charge, because you're just removing electrons from a thing. That's how trivial it is. Now, you can also do this by chemical means, which is an entire field of chemistry that we're going to talk about in 163 when we talk about redox chemistry. So, electrons are actually very mobile. So mobile that they can just leave the atom in the presence of some sort of stimuli. And when that happens, what you create is called an ion. And we're going to talk about ions later today. But an ion is any arrangement that is a different number of electrons and protons. So if I go back up here, and let's just get rid of this number here. And let's say, oh, I had an extra electron in here. So this is now the charge that I see. Well, then I would say, okay, positive 6 and negative 7 has a total charge of negative 1. And so that would be my available charge on that ion. So if your charge is 0, we call it an atom. If your charge is not 0, we call it an ion. Okay? I'm just going to do this just to... Yeah, oh man, it started out so good, but... Now my system is slowing down for some reason. I'll reboot it tonight. Alright, how do you know which atom is which? If I give you an atom that has 6 protons and 6 neutrons, how do you know that it's carbon? Because you could see down here that I wrote carbon, right? Ooh, I don't know what's happening. Interesting. I don't know why it did that. So I wrote that it's carbon, but how do you tell? The answer is that on the periodic table, there is a number, and this number is usually represented in either the top or the top left or top somewhere. And it's going to be an integer. And this number is called the atomic number. The atomic number is just the number of protons it has. And we have defined every combination and arrangement of, or not combination, I guess, but every arrangement of protons to be a given element. If you have 1 proton, you're hydrogen. If you get a second one somehow, you become helium. If you have 3, then you're lithium, and so on, all the way up to 108. Or 118, sorry. So if you have your periodic table, and we'll paste this into the chat real quick. So let me do that. ptable.com. And then I'll do that. There you go, just in case you need it. I would definitely bookmark that link and have it handy for the quiz or the exam. But in case you don't have it today, that's fine. And you can look around and you'll see that on ptable, and we'll capture that on the screen here. Oops, that's the wrong button. ptable. And you can see that, let me get rid of the stuff on the side. On the top of each box is a number, and that is the number of protons that atom has. So if I'm down here on calcium, calcium atoms have 20 protons. Potassium is 19. And because these are all atoms, the number of electrons that they would have is also the number that's shown. So iron has 26 protons and 26 electrons. Oxygen has 8 of both, too. And so on and so forth. So that's the beauty of the periodic table, is we have all of that information, it's just stored in there. Now the other cat is here. What? I fed you guys, didn't I? I think they just want hugs. Krasnik, come say hi. He's going to sit on his box and meow at me. I don't know if you can hear him. We'll see. There is some symbology that is used to describe atoms in terms of just a combination of letters that we can write down, as opposed to, say, a picture. And that symbology is the following. We're going to call the atomic number Z. And like we said before, the atomic number is just how many protons there are. So you're going to write Z equals number of protons. Then what we're going to do is we're going to define a new term. We're going to define this term A. A is the mass number. And we haven't talked about neutrons yet, but we need to include them somehow. So the mass number is going to be however many protons we have added to however many neutrons we have. Now, I haven't mentioned neutrons yet, but because they're neutral and they don't have a charge, if you had 1 neutron versus 10 neutrons, that shouldn't really do much in the way of making the atom electrically unstable. And it turns out it doesn't. So you can have any number of neutrons you want to some extent, and that's sort of beyond the scope of this class, but we'll talk briefly about it. All right. Now, very important, this mass number that we are making here is not on the periodic table. And we're going to talk about that at the end of today, when we talk about how to calculate the atomic mass of an atom. Mass numbers are just a construct. How many protons, how many neutrons, add them together. And you're always going to get an integer, because you can't have pieces of protons or neutrons. They wouldn't be called that if that was the case. They'd be called quarks. Now, when we calculate mass number, remember that mass number is protons and neutrons, and the atomic number is just protons, and it tells you how many electrons there are if we're looking at an atom. So all of the information about an atom can be contained in these two variables, Z and A. And so what we're going to do is we're going to take Z and A, and we're going to create a symbol with an atomic symbol out of them. And here's what we're going to do. For any given atom, or ion, this works for ions too, but we'll get to ions later. We're going to describe our atoms in the following way. First, we're going to take this curly brackets E, and we're going to replace it with whatever element we're looking at for the given problem. So if I asked you a problem about calcium, I would get rid of this E and the brackets, and I would just write capital C, lowercase a. No curly brackets. It's just that when I wrote E, everybody left the E there. And so you just look at the symbol for the periodic table and put whatever symbol that is for the problem that you are given. So this is just a template. The second thing that you are going to do is you're going to add Z in front of the symbol you wrote as a subscript. And Z, again, is the number of protons it has. Next, you're going to add the mass number, which is protons plus neutrons, as a superscript, and it goes right above where you wrote Z. And then finally, you celebrate. Now, this is known as complete isotopic notation. I like to just call it this ZAE notation, or ZAE notation. I don't know. Nobody else calls it that, but I do. So you'll see it in other places. It's just easier to write ZAE notation in a table. Now, if you had a charge, because you were looking at an ion, you could write the charge right here. If you have a neutral atom, you don't indicate anything at all. It's just neutral. So let's do an example here. I'm going to give you sulfur, And this sulfur atom that I'm looking at in this example has 16 protons and 17 neutrons. And so what would we write? Well, first we'd write the symbol for sulfur, which is S. And then for Z here, we would write the number of protons, so I'd go 16. And then if the mass number is 16 plus 17, which equals 33, I would put the 33 up here. And there you go. So that's how we write a complete isotopic notation symbol. You write the symbol, you write Z, you write A, and you're all set. All right, so I have a bunch of these. Oops. And what I want you to do is I want you to construct the isotopic notation symbol for each of these atoms that has this criterion. Now, that's impossible for you to typeset into the chat here, so you'll have to like make up some sort of thing. So like if you did something for like that sulfur that we did there, I don't know, something like that. To just indicate what you have done. But it should look like what we did on the... Oops, hold on. What we did on the previous slide here on your paper. Okay? All right. So go ahead and try to construct these four things. Be careful with the terminology because I have purposely obfuscated it. And I've made some of them like algebra problems. Yeah, you have to do a little algebra today. Gross, right? All right. I'll be back in 5 minutes once I figure out what the heck the cats want. And we'll go over the answers at that time. Go ahead and type stuff in the chat as you do it. And I'll see you in a bit. Good luck. We're all counting on you. One more minute, we'll go over the answers. All right, let's go over the answers here. If I could find my pen. There it is. I actually put the pen back where it was supposed to go this time, and that confused me. All right, so for number 1 here, I have an atom with 25 protons, so that's Z, and 27 neutrons. So 25 plus 27 must equal A, and that's what, 52? And then I got to look up on the periodic table which atom has 25 protons. And so if I do that, and I think I still have this captured, so if I go like this, and if I do that, I find out that it's right here, manganese. So I would write on my isotopic notation symbol, I would write Mn, and there you go. All right, let's look at the second one. An atom with Z equals 37 and A equals 72. Now, you don't have to add these because I've already given you Z and A. So we'll just put them right where they should go. And then I'm going to look up what atom has 37 protons. So we'll do that. So 1, 2, 3, 37. There we go. So Rb, whatever Rb is, turns out that's rubidium. So I'll write that down. There you go. All right. Number 3 is kind of a bit of a math problem. So an atom with the same number of protons and neutrons where A equals 36. Well, if the number of protons is X, and the number of neutrons is some other variable, but it's the same number, we would just call it X also. That would mean that, oops, hold on. X plus X equals 36. Or in other words, 2X is 36. And so X must be 18. So the number of protons must be 18, and the number of neutrons must be 18. And so A is 36, Z must be 18, and then we go look up what atom has 18, and that's argon. That's over here. I would tell you a joke about that element, but all the good ones are gone. All right, for this last one here, one fewer neutron than protons. So we got whatever X is, I've got one fewer of them, yeah? So 2X minus 1 equals 19. And if I do algebra here, 2X would be 20, and then X would be 10. So there are 10 protons and 9 neutrons. So I would do for number 4 here, I would say whichever one has 10, we'd go look it up. And, oops, I got to click on this one. That's neon. That's right here. And so we just do this. Whoop. There you go. All right, lost my cursor. Where did it go? There it is. That's what I want. I want that there. All right, there you go. That's how you do isotopic notation symbols. Any questions, let me know. So sometimes you may have to do a little bit of solving. Remember, algebra is your friend. You might never have thought that before, but in chemistry, algebra is definitely your friend. Or at least your truce-worthy ally, I guess. You don't have to be friends with algebra. You just have to declare a truce and agree to work together. All right, for this next section, we're going to talk about ions. And we're going to change the number of protons and electrons in a given atom so that it obtains an overall charge. So let's talk about how we do that. All right, so we've already said everything on this slide already. We said that opposite charges will attract each other, like charges will repel each other, and that the total charge on the atom is 0. That's cool and all. Now, why do electrons not get pulled into the nucleus? And the answer is it's because of how quickly they are moving. And we're going to draw a little diagram to sort of show this. So let's go over to here. So the best model that we have for this is the sun and the earth. So if I draw like this, there's the sun, and it's happy to see us. There's the sun. And here's Earth. And we're just happy to be here, right? Now, there is some force that pulls the Earth toward the sun, and this is the gravitational force, right? And so, in other words, if this was the only force present, then the Earth would go hurtling into the sun, and we'd all die, right? That looks entirely too happy. I was going for, like, that emote. That's what I was going for. Now, fortunately, the Earth has momentum. For instance, if we were to turn off the gravity of the sun by, like, snapping our fingers and invoking magic or whatever, the Earth would not just hover in space. It would go catapulting off in a line, kind of like if I was holding a yo-yo on a string and swinging it around and then I let go of the string or the string snapped. The Earth would just go hurtling off in whatever directions. Now, the result of the sum of my momentum and also gravity pulling the Earth towards the sun is we get this sort of orbit. And wow, I totally missed. Hold on, let's do that again. There we go. And our orbit is very regular. It's so regular that we can make very accurate calculations and predictions on where things will be at any given time. Now, this is assuming that nothing comes along and disrupts the orbit. So, like, if a really giant, like, mass, like another star or something Jupiter-sized, for example, were to just pass by the Earth within a relatively short distance, it would screw up our orbit because the Earth would be attracted to it too. And as a result, that could be disastrous. So let's hope that that never happens. But the reason that I bring that up is not so that you have trouble sleeping at night, like, oh no, rogue planet might knock the Earth out of the orbit. Ah! No, that's not why. It's because if we go to this model here, here's my proton and here's an electron. These would be attracted, but the electron also has its own momentum, and so its path would resemble that of the Earth going around the Sun if there was only one proton and one electron. But the second that you add another electron to it, you get this very chaotic arrangement. I don't know why it's not drawing now. There we go. Of forces in a diagram. And then what ends up happening is that because these two repel from each other, anytime they get near each other, the orbit would change. And it's always going to be relative to the other thing. And so this is where your electron cloud pattern comes from. It's essentially a random path. So this is why electrons do not follow strict orbits. It's because the system that would generate such an orbit is extremely simple. You have one major force and that's it. And in the planetary system, that's this. But in the atom, all of the protons and electrons have the same magnitude of force. It'd be like a bunch of suns trying to orbit each other. You get a very weird pattern because they'd all be attracted to each other and they'd all bounce off each other and swing around at weird angles and so on and so forth. And that's what we experience with the atom. So that's my best way of explaining how electron clouds behave and why the electrons don't just get sucked into the center and neutralize each other. Basically, if you put an electron and a proton together, you get a neutron. That's nuclear physics, though, and we'll talk about that never, really. Which is too bad, because nuclear physics is fun. Alright, let's talk a little bit more about ions. We're going to define these terms, anion and cation, as the following. If you have more electrons than protons, we're going to call it an anion. And if you have fewer electrons than protons, we're going to call it a cation. So, those are the words you want to pay attention to. More electrons, anion. Less electrons, cation. And the way that I remember this is if you write the word cation, but you write the T as a positive symbol, then the charge is right there in the word. And then there's the other way to remember it. Cats have paws, positive. Which makes Grumpy Cat upset. I don't know. I think that mnemonic is just really silly. So, cations are positive. Anions are negative. And you just have to remember that anions are the other thing, if you remember what cations are. And that's generally good enough. Now, there is an issue that you have to remember. When you are dealing with adjusting the number of protons and electrons, and that is, when you take away electrons, you end up with a more positive thing, and that might seem really weird. But what's actually happening here is if you are subtracting electrons, which are negative, it's like subtracting negative numbers. If I do this, 4 minus negative 2, remember that in math, that's the same thing as doing this, right? So if I have a charge of 0 and I remove 2 electrons, that's the same as this sort of operation, and this would be the charge that's left over. So be mindful of that. That's a really common mistake is I say, okay, I remove 2 electrons. What is the result, or what is the outcome? Make sure you have the correct symbology on your charge. All right. So that's our intro to how to create ions. When we come back from the break, because it is break time, so we'll put the break timer on the screen here. When we come back from the break, we're going to start constructing tables that have information about ions in them that we can use to convey various properties. So I'm going to start this timer here, and we're going to go back to Zelda Wave and enjoy some classic remixes from a game that is probably older than most of you guys. Alright, we're back. We turn the Song of Storms down here. Alright, there we go. Alright, so let's continue our discussion about making ions real quick. With some examples here. Ooh, yeah, it's kind of spooky. If you haven't played Ocarina of Time, I definitely recommend it. How you get that song is kind of weird. Out of context, it won't make any sense, though, so I won't bother. But alright, so let's talk about making ions. So here I've got a sodium atom shown on the screen here in a little cartoon. And you'll notice that over here, I have my electron cloud drawn as this sort of translucent purple bubble, I guess we'll say. And I take away an electron from it to form the sodium plus ion. And you'll notice that my electron cloud gets smaller. And what this basically means is that because I have protons in the nucleus pulling my electrons, if there are fewer electrons to pull, they get closer to the nucleus. And this is a thing that happens in atoms all the time. If you change the number of electrons, you change the distance on average that those electrons exist at. And that'll be helpful in 161 when we talk about quantum mechanics. Because all quantum mechanics it really is just what are the results of charge? And so understanding these fundamental principles really will help you later on. Right now, they're not going to be super useful for us, but just keep that one in your back pocket. Electron cloud shapes can change based on adding or removing electrons. So if removing an electron shrinks it, what do you think happens when I add an electron to, say, chlorine? Well, it gets bigger, like you'd expect. So the electron cloud grows as electrons are added. And the reason for that is more electrons around a nucleus means more places that the nucleus has to pull and use its charge, because there's only so much charge available, right? The analogy that I can think of is, imagine you're going to the dog park, and you have 2 dogs to watch, but you don't want them to get too far away from you, so you shout at them when they're too far away. On average, they won't get too far, because there's only 2 of them. But now imagine you had 7 of them, because I added 5 dogs. Now you have to shout at all of them, and on average, they will get farther and farther away, because your attention is now split across 7 dogs instead of 2. That's how it works for atoms. The charge is spread across however many electrons there are. And if there are fewer electrons, it can pull them in closer. And if there are more electrons, it can't hold on to them as well. All right. Now, when you write the charge on an ion, we write it as a superscript after the symbol. So this would be a chlorine atom, as written. This would be a chloride ion. You'll notice that I said a different word, chloride versus chlorine, and we'll get to that in unit like 12 or so, what the naming conventions are. For now, you just need to know the symbology. Now, could I make a chlorine plus ion? Sure, but what I would have to do is I would have to remove an electron, and I'd get 17 protons and 16 electrons. There is no restriction on whether something is plus or minus. It is just a matter of how many electrons did you add or remove. Now, is there a preference? Absolutely. We're going to talk about that preference later. Now, what's the difference in terms of the behavior of ions versus elements? So if I have sodium metal, so this is atomic sodium right here, sodium metal will detonate in water. But sodium ion is very stable. In fact, sodium ion is in your water right now. It's the sodium in table salt. And we're going to talk about that in 161. But the reason for this is really just due to the fact that having certain numbers of electrons results in different chemistry. And for now, we're not going to really correlate number of electrons with result, but we are going to definitely find patterns. And these patterns we're going to explore in a little more detail in, I want to say it's Unit 9, when we talk about the octet rule. We'll get to that. Now, on the board here, I have, I should have had a banana for breakfast, actually. I bought them for this reason. I have a banana, and bananas are a good source of potassium. Chris, get the banana. Potassium, right? That was for anyone who's played Deltarune. Now, in the banana, would you have atomic potassium with no charge, or would you have ionic potassium, which ends up being this charge, K+. The K is for Chris, I guess. I don't know. And it turns out, well, we already know that this one detonates in water, right? So it must be this one. In fact, many ions that we're going to observe are going to be quite inert. Much more so than the atomic form of the element. All right. Oops, that's not what I meant to do. Trying to clear all the ink so you can read that. All right, let's do some examples here. So this is all symbology. So whether or not this actually happens is irrelevant. We are just doing conceptual examples. So let's consider I have a nitrogen atom. So here it is. And I want to add 3 electrons to it. What would you write for the symbol? Well, if I'm adding 3 electrons, so 3 electrons would be that. And then if I'm adding them, electrons are negative, so I'd put a negative charge after it. Maybe not that big, but that's okay. How about this one? I want you to type in the chat the best that you can what ion forms when you remove 2 electrons from a calcium atom. I'll give you a minute to type that in, however you can think to, and we'll go over the answer. All right, and that's the correct answer. Very good. We're going to take 2 electrons away. Electrons are negative, so removing 2 negatives gives you a positive 2 charge. All right. Now let's work backwards. How many protons and electrons does this ion have? So I'm going to leave you to your own devices to calculate this. You're going to need to refer to p-table, which I think the link is still on. I'm trying to. There it is. Yeah, it's still on the screen. So click that if you need it in the chat log. And enter the number of protons and electrons in the chat based on this description. All right, so let's do the calculation here. So we're going to get this back on the screen. And of course, nothing is working because I've minimized the periodic table. Oh, no, the periodic table fell asleep. That's why. So there it's back now. Sorry, my tabs garbage collect and sleep after 10 minutes, so it breaks all my links here. Okay, so we'll find iron. I gotta click on, oops, that's not what I want. We click on, there we go. So there's iron. I clicked on it. There it goes. Okay. And you'll see that it has 26 protons. So we'll write that down. If I had a cursor, though. There we go. Oh, that would be why I don't have a cursor. Okay. And we'll notice that there are 2... Oops, hold on. Can't see what I'm doing here because I didn't remove that. There are a 2 positive charge present on my ion. There is a 2 plus charge. And so what that means is I must have 2 fewer electrons than protons. So the number of electrons I must have would be 24. There you go. So that's the sort of logic that you would follow through with this type of problem. Number of protons is easy. You just look at the periodic table. Number of electrons you can calculate based on the context of the problem, okay? So always start with the number of protons and then work your way from there. All right, on the board I have a table, and what I want you to do is I want you to fill in the blanks in this table based on what's shown. Now you're going to notice that on my isotopic notation symbol, I've started to add in the charge. So go ahead and do that on your isotopic notation symbol, right where we would normally stick the charge, and fill out all of the other things based on the information that's already there. So let's do this first one as an example. Here I've got titanium. Titanium, according to the periodic table, if I go back to P table, titanium's right here. It has 22 protons, so we'll go back to our table here, and we'll fill that in, 22. Its symbol was Ti, and then we'll go Z. A would be protons plus neutrons added together. And then number of electrons would give it a charge of that. So that's what I want you to do, is fill in the table like that based on the information that is present and shown. You could type that into the chat as best as you can, and we'll go over the answers shortly. Okay, see you in a little bit. 1 or 2 more minutes, and then we'll go over the answers. All right, let's go over the answers here. So we got this BR thing right here, but we don't have the name for it. So we're going to have to go back to the periodic table, boop, which is right here. We got to find it. So here's BR. So that's bromine. Boop, there we go. Get rid of that. So we'll just, oops, well, I guess we'll advance the slide here. We'll just write that in, bromine. And I know that it has 35 protons because the periodic table says that, but also because it's right there. I've already indicated the number of neutrons. Now I gotta do electrons. I have 2 more electrons than protons, so that would be 37. That would give me my 2 minus charge. And we're all set there. All right, for the third row, how do I know what element it is if all I have are numbers? Well, remember, the atomic number is how many protons something has. So if I go back to the periodic table, boop, and I look for what has 6, there it is. So this is carbon. So we'll go back over here, and we'll write that in, carbon. And then I just need to write an A and then whatever the charge is. So if I have 7 protons, protons plus neutrons would give me the mass number. And then protons and electrons considered together, I have 2 more electrons than I do protons, so I'd do that. All right. Next we got lead. Lead has 82 protons as shown right here, so we'll just write that in. How many neutrons are there? Well, Z, or not Z, sorry, not Z. A is the number of protons plus neutrons, so 82 plus what gives you 105, or 205. And that would be 123, I think? Yeah. And then finally, how many electrons should I put here to get a charge of 4+? Well, I need 4 fewer electrons, so 4 fewer than 82 is 78. All right, and then finally, for down here, we could look up the name of this. Ruthenium. I'm drugged my pen incorrectly. There we go. Here's the number of protons. That's Z. So we'll put that right there. A is the number of protons plus neutrons. So 44 plus what is 94? We'll just fill that number in. And then finally, right here, I have 3 fewer electrons than protons, so that must be the number I put in. There's a question, I can't read it because my chat got buried. Let's see here. Explain the reasoning for the negative and positive number that decides the number of electrons. Yeah, so remember that the charge tells you the overall result. So if I go over here... Oh, we still have this on the screen. Let me get rid of that. All right, so if we do... This isn't actually doing anything. There we go. Yeah, let's look at the carbon here. So if I have this as my ion, then what this is saying is 2 more electrons than protons. And so I know that I have 6 protons because it's carbon, right? And that would have this charge. If I have 2 more electrons, then I would have this many electrons. And when I combine these charges together, this is the result. So if you just see Hg with a minus, that means 1 minus. Yeah, so if you have a charge that only looks like this or this, these are assumed to be 1 minus or 1 plus. However, it is convention to not write in the 1, just to save on ink, I guess. I'm not really sure why we don't do that. Sorry, drinking my water there. So if you just have 1 of a charge, you just do plus or minus. Now, if you see C-13, that's actually something different. We're going to talk about that in the next section. That's isotopic notation there. So if you see something that looks like this, what this is actually implying is carbon 13. And that has a very specific meaning that we're going to talk about right now, actually. All right. Any other questions, let me know. Let's talk about isotopes. So we've talked about different combinations of protons and neutrons and electrons today. But we're going to focus on what part the neutron has in all of this and discuss atomic mass. Because, as you've noticed here, in these examples, we focused on protons and electrons so that we could determine the charge. But the neutrons we just sort of left to their own devices, right? Like, okay, sure, there's 19 neutrons. Why? Well, it kind of just said so, right? And the reason that we aren't specific on neutrons is because in chemistry, we don't really give a shit about the neutrons. They don't have a charge. So they just kind of hang out. Like, whatever, do your thing, neutrons. Sure. There could be 12 of them, there could be 70 of them, there could be 1. We don't really care. We care about the charge, because chemistry is all about charge. Physics cares very much about the neutron, because mass and velocity and kinetic energy and all that are very important when doing experiments, but we're not doing physics so much. We're applying one specific part of physics, which happens to be charge. So we're not going to really care about neutrons in most applications. But there is one application that it is very important, and that is, what is the weight of something that is macro scale? Because if there are lots of neutrons, those masses will all add up. So we need to consider some facts about neutrons in order to understand their use. So I'm going to put some ions on the screen. Actually, sorry, these are not ions. These are all atoms. These are all neutral. And so what we want to do is we want to count the number of protons, the number of electrons, and the number of neutrons. And you'll notice my symbology there. I have a P with a plus, that's proton, an E with a minus, that's electron, and an N with a 0, that's a neutron. If I just write N, then it looks kind of like a variable. So the 0 is there to help indicate, oh, that's referring to a neutron. And so these are all borons, so they're all going to have 5 protons, and that's pretty straightforward. And if they're all neutral, they all have 5 electrons too. But how many neutrons do they have? This one has 5 because I can tell the difference between Z and A here is the number of neutrons. Protons plus neutrons equals mass number. So 5 protons plus some number would give us 10. That must mean we have 5 neutrons. And then over here, we would have 6 and then 7. Now, what's the difference between these different atoms that we have drawn here? In terms of chemistry, there isn't any. They're all boron. They'll all react like boron. But this boron is heavier than this one. And so we have a special sort of circumstance here. And that circumstance is that I have different atoms that have the same number of protons and electrons, but different numbers of neutrons. Or in other words, same Z, but different A. If you are looking at a collection of atoms, and those atoms have this condition, same Z, different A, then the term that we describe those atoms as is called isotopic, or isotopes. Now, specifically, these are isotopes of boron. And you can have any isotope of boron you want with any number of neutrons. So, for example, this is an isotope of boron. This would be an isotope of boron. We've already done that one, so there we go. I mean, that's going to be super unstable, but whatever. But this would not be an isotope of boron because that's not boron, that's beryllium. Okay? So I can change the number of neutrons to whatever I want and get a different isotope. But it has to stay 5 protons to be an isotope of boron. And I can do this with any atom I want to. There are many isotopes of hydrogen. Hydrogen with 1 neutron, hydrogen with 5 neutrons, hydrogen with 50 neutrons. Those are all isotopes. But if I change any other thing, then I get a different atom. All right. How many isotopes naturally occur? Naturally occurring isotopes are what we refer to as stable. If you are the sort who has looked at anything chemistry, You've probably heard of the words stable and unstable. Unstable being radioactive. What does this mean? A stable isotope exists on a time frame that is so long that being around it is essentially safe. In other words, isotopes fall apart into radioactive particles all the time. But the more stable it is, the less likely that is to occur. For instance, carbon-12 and carbon-13, are relatively stable compared to something like, say, uranium or cesium or iodine, specific isotopes of those. Most elements have between 2 and 10 isotopes that are stable. They stick around for a long time. And when I say a long time, this is what I mean. At least 4 billion years. That's an awful specific number, it turns out, and there's a reason for that. Now, you can make any isotope that you want to, but those that don't occur naturally are unstable, and the reason for that has to do with this number. And this is sort of a chemistry fun fact. This number is roughly the same order of magnitude as the age of the Earth. The Earth was formed roughly this many years ago. Probably a little more, but on the same order of magnitude. So it'd be between 1 times 10 to the 9 and 1 times 10 to the 10 years is probably about how long ago the Earth was formed. When the Earth was formed, it was formed with a bunch of elements. And if those elements were radioactive, and they lasted less than this number right here, we would not observe them today. And thus, they would not be stable or naturally occurring. So any isotope that has a life expectancy of less than that number is unstable, and it will not appear in nature. It's already irradiated away. So in order to make it a synthetic isotope, you have to go to the lab and cram together a number of protons and neutrons, and electrons, of course, to get the isotope you want. Now, if you are curious, and I have to actually look this up here, table of the nucleides. Let me see if I can find a website that has this. I want to zoom in more. Yeah, this'll work. It's real slow, but I can make it work. I'm just trying to scroll this all the way down here, though. There we go. Okay. Can I just delete that and then... this'll work. Okay. So let me get this on the screen here. So this is what's known as the table of nucleides. And we really only want to see this part. All right. And so what you can see here is that I have, on the y-axis going up, I have atomic numbers. So that's why this is increasing. I've got hydrogen, helium, lithium, beryllium, etc. On the x-axis, I have number of neutrons, which goes 0, 1, 2, 3, 4, etc. over in this direction forever. And this is every combination. Down here on the bottom row, where it says N, I have no protons and 1 neutron. So this is a neutron right here. But here you can see that I have hydrogen, 1 hydrogen with, or hydrogen with 0 neutrons, then with 1 neutron, 2 neutrons, 3 neutrons, 4 neutrons, 5 neutrons, and so on and so forth. Now, if I click on this, I'm trying to find its half-life. This is all energy. This is not at all what I want. I should have looked at that. Maybe I need another chart here. I'm on the segue for a little too long here. Talking about radioactivity when we're really just not going to do much with it. Oh, this only has abundance. I want... Oh, there we go. Okay. Yeah, that's what I want. Okay. So I got a better chart here. All right. We don't care about that stuff at the bottom. All right. So these are all the different isotopes that exist. The ones that are in black are stable. So you can actually see right here, there is a list of how long things last. 10 to the 14 years. That's a very long time. Versus 10 to the minus 12 seconds, which is a very short time. Hydrogen is stable. It lasts virtually forever. Hydrogen with a neutron is very stable, but hydrogen with 2 neutrons lasts about 12 years on average. Hydrogen with 3 neutrons, which would be hydrogen 4 here, lasts on average 139 yotta seconds, which is times 10 to the minus 12 or so. And then these last even less time. All right. There are certain isotopes that are stable for certain combinations of neutrons and protons. If you have too many neutrons, the neutrons fall apart. They turn into protons and electrons. If you have too few neutrons, protons start to repel each other. And thus the nuclide doesn't exist. Now, if I zoom this out, there are tons of isotopes that are known. And the color-coded chart here tells you which ones are the most stable, which is the darker colors, and which ones are the least stable, which is the lighter ones. So there are tons of isotopes that exist in nature. The black ones are naturally occurring. Any other color is synthetic and would have to be made. All right. So why did we go on that little discussion? It's just to let you know that you can make isotopes however you want to, but certain ones don't exist naturally. Now, all of these isotopes are going to be named in the following manner. They're going to be named with their chemical identity, a hyphen, and the mass number. So, for example, right here, this has mass number 12, so this would be carbon 12. This one over here is carbon 14. And you've probably heard of carbon 14 from carbon 14 dating. And that's because carbon 14 is radioactive. It lasts about 7,000 years. And since we're almost out of time anyway, I might as well spend the last few minutes talking about carbon dating because it's neat. So let's suppose, I think we'll just write 7,000. Let's suppose that you are an old creature, such as, say, this dinosaur here. There we go. And here's his long tail. Oops. There we go. Oh, and he needs an eye. There we go. There's my dinosaur. And so he eats leaves. Because he's an herbivore. And this is my tree, I guess. My tree has carbon in it. And some of that carbon in there is carbon 14. Carbon 14 is interesting. It forms from high energy photons interacting with, I want to say, nitrogen. Maybe not photons. It might be like nitrogen absorbs a neutron from space, because the sun is just spewing neutrons and stuff like that. And then that causes it to be unstable, and then it reverts to carbon-14 or something like that. I don't know. However it happens, this is a naturally occurring process so that carbon-14 is formed, and it incorporates itself into plants, and then those plants are eaten, and then the dinosaur has carbon-14 in it. Now, the dinosaur is going to be eating food and constantly replenishing the amount of carbon inside it. So the amount of carbon-14 inside an organism is constant while the organism is alive. And if we know what that amount is supposed to be, then we can say, okay, well, if carbon-14, we'll call this time 0, decays over time, and we know that every 7,000 years, half of it's gone, and then half of it's gone, and then half of it's gone, and then half of it's gone. We make this little sort of graph. And we can say, okay, this is how much it has right now. How long ago was it alive? And we can do the calculation. So isotopic dating is super useful for things like archaeology. You can determine how old anything is if it was an organism that incorporated carbon into it using carbon-14 dating. And you can actually be quite precise with that. Plus or minus 100 years. If you're only looking back, like, say, 10,000 years or so. If you're going back millions of years, then you're probably within a half-life. But still, getting within 7,000 years of 65 million is pretty darn good. So that's why we care about isotopes. This is going to be important for Orca students, I guess, if you're going to go into, like, trying to isotopically date stuff that, like, lives on the seabed floor. I'm not sure if you can use the same isotope, but I suspect that it would work similarly. So maybe that's an interest to you. You want to find out how old these starfish really are, or something like that had died or something. I don't know. All right. So we're out of time here, but these examples are pretty trivial. You can just use the A notation to indicate the mass number, and so you could say, oh, okay, well, if A is 25 and I have 12 protons, I must have 13 neutrons. And so on and so forth. Just a second, I'm just checking something here. Okay, that's where I want to stop there. I'm going to leave these examples for you to do on your own. We'll start on Tuesday with them. Last thing we'll talk about are isobars. Isobars are just atoms that weigh the same. So same A but different Z is an isobar. And other than that, I really don't care about isobars. We're not going to use isobars in this class. It's just kind of interesting that if I had this and this, they are chemically different. Because one is carbon and one is nitrogen. But physically, they're nearly physically indistinguishable. Because remember, the mass number is just how much mass there is. Now, there are slight differences that we're going to talk about tomorrow. But that's really why we care about isobars. If you have isobars, you cannot separate them through weighing because they weigh the same, right? You have to use them. You have to do chemistry to separate them. But other than that, we don't care. We care much more about isotopes because those are common within a given element, and that's going to affect our ability to use the periodic table, which, again, we'll talk about tomorrow. So go ahead and look over these examples tonight. We'll start class with these tomorrow and then go over the answers, write the isotopic notation symbols, and then categorize them as isotope, isobar, or neither. But other than that, we'll finish... Oops, I hit the wrong button. Hold on. Well, I'm going to hit that and it's going to go blank, but that's okay because we're going to go over here. We're going to finish Chapter 7 tomorrow. And then we'll do Unit 8. And Unit 8 is very, very short. It is basically, this is the periodic table. This is what groups and periods are. The end. So we probably won't have to use Wednesday for lecture. If we do, it's still there. And then Wednesday's our review. And then Friday, your midterm is going to be... Sorry, I hit the mic there. Your midterm is going to be Units 1 through 8. So that's all on the way. Make sure you don't fall behind. I do realize you have a lot of work to do this week. But make sure you're also asking me questions in the Discord or over email. Let me know if you have any questions about anything, and good luck studying for the exam.